All right, this is going to be the video for section 4.6 in differential equations, variation of parameters. Okay, this is another procedure we can use when we have a right-hand side, which is non-zero, a non-homogeneous differential equation. And actually, in the last video, I don't think I mentioned that there was a restriction on the method of undetermined coefficients, and that was that method will only work if the coefficients of all of the derivatives on the left-hand side are constants, so you can't actually have functions. But this method we're going to learn today is more flexible, more general, and so you can use it in a wider variety of cases. So if we have a non-homogeneous differential equation like this, I don't think I made it clear enough, but we can't use the method in 4.4 because these coefficients are not allowed to be constants. This is a 1, that's fine, but you can't have functions here as the multiples of the left-hand side coefficients. But we can solve that with the equation we have here. Now, this procedure is going to seem very convoluted and arbitrary, but if you're interested in the derivation, I do have a separate PDF for section 4.6 that explains and shows the derivation of the method. We're just going to focus on how to use the method. All right, so the method works like this. First, you find in some way the solution to the corresponding non-homogeneous equation, so the YC solution with its constants. Okay, then you take your original differential equation, the non-homogeneous equation, and you divide by the leading coefficient of the highest order derivative to put it in standard form, and then you name the right-hand side f of x. Okay, and then you postulate a particular solution that's of the form some function u times whatever you got in your characteristic solution here, corresponding solution, and then so basically you take every term in your corresponding solution and you tack on a function u, kind of like when we did reduction of order earlier. Okay, so these are currently unknown functions, right? And then you use the following fractions and determinants essentially to use Cramer's rule to solve a system. It turns out that the derivative of this u1 is going to be, if you form the determinant that's found by taking the function y1 and y2 in the row, and then take the derivatives here like you're forming a Wronskian. In fact, this is the Wronskian of these two solutions. Okay, and then you use Cramer's rule to divide by, for u1, replace the first row by 0, and then put the right-hand side after dividing by the leading coefficient here in this position, and leave the original y2 and y2 prime here. That computation will give you the derivative of the u1 function. It's crazy that that works. If you're interested in seeing why, read the separate PDF. And then for the u2 prime, we do the same determinant on the bottom, but on the top we replace the second column with 0 and f1 and f of x, the right-hand side. That gives you u prime for 1 and u prime for 2. So to find the corresponding functions, we have to take the antiderivative of each of those. That will give us the u1 and u2. So then you just tack those on to the same constants here, or the same functions you had in your yc to form yp. And then you form the complete solution by taking your yc and adding your yp terms. Right? So it's a little different. It's more flexible. So why would we not always use it? Well, the pros are you can solve differential equations with non-constant coefficients that are non-homogeneous. It works in some cases where the right-hand side, remember we had some limitations on the right-hand side, like we couldn't have anything but sines and cosines. We had to have polynomials or exponentials or sine and cosine. This will also work in those cases. You actually don't have to worry about that absorption issue that we had in the undetermined coefficients method. You can solve everything we already know how to solve, in fact, using this method. But the con is it usually takes longer than earlier methods. And sometimes the integrals at the end to undo the u prime and u2 prime, sometimes those integrals are really hard to find. So it's more general and it works in a much wider variety of cases, but it's harder to use. So we really only employ it when other earlier methods have not worked. Okay, so we're just going to go through some examples of this. Let's say we had this differential equation, second order, right? The first thing we're going to do is solve the corresponding homogeneous equation. So y double prime plus y equals 0, right? This one I could solve because this one happens to be a linear with constant coefficients, so I can use the auxiliary equation method. There's no derivative here, so that would be 0. I'm sorry. That would be 1, but without an m. So 1 times m squared, 1 times just y to the 0 or m to the 0, which is 1, equals 0. So we would get m squared equals -1, which ends up being that m is going to be plus or minus the square root of -1 or plus or minus I, right? That means we have a complex thing where alpha is 0. So my alpha plus beta, beta is 1, alpha is 0. And that means that the YC is going to be some constant times e to the alpha 0 times cosine of beta, which is 1x, plus c2 e to the alpha 0, or alpha x sine of x, right? But these e to the zeros are 1, so really the YC is C1 cosine x plus C2 sine x. Okay. All right, so now what we're going to do is we're going to postulate a YP, but what it's going to do is just take this form and replace these constants with functions now. So YP is going to be U1 cosine x plus U2 sine x, where these u's are not constants, they're going to be functions. So we're going to use this form for finding what U1 is. First, we can use a form for finding what U1 prime is. U1 prime is given by a ratio of determinants. And so what we do is we take these two functions here and we load them into the first row of a determinant matrix. And then we get ready to do the Wronskian, so we take the derivative. So the derivative of cosine is negative sine. The derivative of sine is cosine. And then in the top, we take that same matrix, but we take for the first one, the first column, and replace it with 0, and then the right-hand side. This is my f of x. If you had a leading coefficient here, you'd have to divide by that first to get this. So that means we're going to get tangent of x here. And then this is still sine x, cosine x over here. Okay, so we'll compute these derivatives. So this derivative on the bottom turns out to be cosine squared minus negative sine squared, which is nice because that turns out to be 1. And on the top, we have 0 minus sine x tangent x. Okay. So since this bottom is 1, this first u prime here turns out to be negative sine x tangent x. Tangent x. Okay, and we'll do the same thing for u2 prime, except we're going to have the same matrix here for a determinant on the bottom, which is the original Wronskian. But this time we're going to replace the second column with 0 and tangent x. We still have cosine x, negative sine x from the bottom there. The bottom is still going to turn out to be 1. We didn't change that, but now I've got cosine x times tangent x minus 0 on the top. So this one ends up being cosine x tangent x. Okay, so now that I know what u1 prime and u2 prime are, I can take the antiderivatives of these. So u1 prime is the antiderivative, I'm sorry, u1 is the antiderivative of u1 prime with respect to x. And so I'm going to have to take the antiderivative of this. So this is going to be negative sine x tangent x dx. All right. So, well, let's see. There's actually an identity that says, we can use some identities, I think, to put this in another form, so we will be able to solve this, because this is not easy to solve. So let me play around here with some identities. What is negative sine x tan x? Let's just do that on the side. Can we rearrange it? Well, the tangent can be replaced with sine x over cosine x, right? So this is definitely negative sine squared x over cosine x. That would be another way to replace it, right? And then sine squared, I also know that sine squared x plus cosine squared of x equals 1, which means sine squared of x is really the same as 1 minus cosine squared of x. So I've got negative 1 minus cosine squared of x over cosine of x. And what that means is this would be negative 1 over cosine, which is negative secant x. Negative negative is plus cosine squared x over cosine x is cosine x. So the reason I'm doing this is because this, rewriting it this way, separates into two terms that each have only one trig function. So the next thing I'm going to do here is replace this with this whole thing here is the same as negative secant x plus cosine x, which means I can now split this into two separate integrals, right? So by table now I can look up that the antiderivative of secant of x turns out to be the natural log of secant of x plus tangent of x, right? And then we know that the antiderivative of cosine is sine. Okay, so that's this. So that's what u1 is equal to, okay? And then we have to do the same thing and do an antiderivative here of u2. So u2 is going to be the antiderivative of u2 prime, and that's the antiderivative of cosine x tangent x this time. So this is the downfall of this method, is unfortunately it often results in things that are complicated. But actually, if we do some identity work here, what's cosine x times tangent x? Well, tangent x can be replaced by sine x over cosine x. So these cancel, and this is in fact just the antiderivative of sine x, which would be negative cosine x. Okay, so u2 is that. And that means that I can go back up here to my particular value and fill in those values here to find that. So I know that yp is going to be u1, which is negative natural log of secant x plus tan x plus sine x times cosine x plus u2, which is negative cosine x times sine x. And then that means that our general solution, I'm not going to write it completely, is going to be whatever we got for yc plus that yp. So it'll be this plus this. So I guess we could write that all out. Let's do that because there might be some things that happen here. Yeah, let's write that out. In fact, actually, if I were to multiply this out before we do that, let's work with yp further. So what is yp? Yp, if I multiply a cosine in here, I'm going to get negative cosine x natural log of the absolute value of secant x plus tan x. I don't think I can do much with that. But then I've got plus a sine x cosine x. And then minus a sine x cosine x. So this is definitely true that these will cancel. So that's yp. Okay, so now I can write my general solution. My general solution is constant 1 times cosine x plus constant 2 times sine x plus my general solution, or my particular solution for the right-hand side being non-zero, which is minus cosine of x times the natural log of the absolute value of secant of x plus tangent of x. That's the final solution, general solution. All right, so a lot of writing, a lot of derivatives, and there's all kinds of stuff going on here. Let's just work a few more examples. What about this one? So we've got a second order differential equation with a right-hand side. Let's see. First, we'll solve the corresponding equation. So that's going to be m squared minus 9 equals 0. This is going to be m squared equals 9, so m equals plus 3 or minus 3. These are real solutions, which means I'm going to get that the C solution is a constant times e to the 3x plus a different constant times e to the negative 3x. Okay, and that means that our postulated solution for yp is going to be an unknown function u times 3x plus a different unknown function u2 times e to the negative 3x. And then we use this memorized formula, or we'll probably give you something on the test for this because it's a lot to memorize. We're going to do the Wronskian down here of these functions. So we have e to the 3x, e to the negative 3x, and then the derivatives of that, which would be 3 e to the 3x and negative 3 e to the negative 3x. There's the Wronskian. Okay, and then we have the Wronskian on top, except the first column is replaced with the right-hand side in the second position. So 0 and then 9x. Let me write that as 9x e to the negative 3x. And then here we have the same original here. So e to the negative 3x and negative 3 e to the negative 3x. Okay, so what's on the bottom here? We've got a negative 3, and we've got an e to the negative 3x times an e to the 3x. So when I add these together, they sum to 0. E to the 0 is 1, so this is just negative 3 minus, and then this is going to be 3 times this, which is also going to turn out to be e to the 0, which is 1. So we end up with just negative 6 on the bottom here. On the top, we have 0 minus 9x, and then we have e to the, let's see, negative 3x times another e to the negative 3x. So when we add negative 3x and negative 3x together, we're going to get e to the negative 6x here. So this is negative 9x e to the negative 6x. So this is going to be positive 3 halves x e to the negative 6x. That's what u1 prime is. Okay. And then for u2 prime, we have the same Wronskian on the bottom. I'm just going to write it as negative 6 because it doesn't change. But what's going to happen is this column is going to become the 0 not right-hand side. And this one will be the original column here. So I'm going to have, let's see, this times this is 9x, and then this and this will add to 0, so e to the 0 is 1 minus 0. So this just ends up being negative 3 halves x, right? All right, so now we can do our antiderivatives. u1 is equal to the antiderivative of u1 prime. This one, we're not going to have to resort to a table, but we are going to have to do integration by parts. So let me move the 3 halves outside. X e to the negative 6x. Maybe we could do, let's make u equal to x and dv equal to the e to the negative 6x dx, which means that du is equal to dx, and the v equals negative 1/6 e to the negative 6, because you divide by the negative 6 constant, right? And so then we go uv minus integral v du, which is negative 1/6 x e to the negative 6x minus integral of v du, which means I've got negative 1/6 x e to the negative 1/6 x plus a sixth, right, bringing this out, and then the integral again of e to the negative 6x. So this ends up being, let's see, when we divide again by this 6 and negative 6, we're going to get negative 1/36 e to the negative 6x. And then all of that is times this 3 halves. So u1 is equal to, let's see, 3 halves times this, let me write it out, 3 halves times negative 1/6 times x e to the negative 6x, and then I've got plus 3 halves times a negative 1/36, and then just e to the negative 6. So this is going to be negative, and then this will be 1/4, right? Because this will cancel to a 2, x e to the negative 6x. And then let's see, we've got negative, because this one's negative. So 3 over 36 is 1 over 12, so this will be 1 over 24 e to the negative 6x. So that's u1. Okay, and then u2 is going to be the antiderivative of u2 prime, which is negative 3 halves x. So negative 3 halves x. The antiderivative of that would be negative 3x squared, right? Is that right? No. Negative 3/4 x squared. There we go, negative 3/4 x squared. So that's much easier, okay? And then that means that our predictor solution is going to be, so yp, well, let's do it down here. We're in a room. Yp is going to be u1, which is negative 1/6 x e to the negative 6x minus 1 over 36, just e to the negative 6x, and that's going to be times an e to the 3x. And then plus u2, which is negative 3/4 x squared times e to the negative 3x, which I feel we can do some simplifying there. If we multiply the e to the 3x in here, I've got a term which is negative 1/6 x times negative 6x plus 3x is a total of e to the negative 3x's. Then I've got a minus 136, and then this plus this also e to the negative 3x, right? And then here I've got, let's see, minus 3/4 x squared e to the negative 3x's. So it's okay to combine like terms within the yp, but what you shouldn't typically see is absorption between this and the yc. So now the general solution will be the yc terms, which just have constants here for multipliers. So constant 1 times e to the 3x plus constant 2 times e to the negative 3x. And then we can tack on this, which will have functions here. I guess we do have one absorption here, and that's actually okay. 1/6 x e to the negative 3x minus 136 minus 3/4 x squared e to the negative 3x. So it is okay to have absorption here, either within yp or even between, because I know this is the solution for the book. So if I think about this is a term with negative e to the negative 3x, and so is this. These things together combine to form some new constant. In fact, what the book does in their solution is they just write this as c1 e to the 3x plus some new constant c3, which is c1 minus 1/36. And then they have their term with an x e to the negative 3x, and their term with the x squared e to the negative 3x. That's the final solution. All right. Okay, those are two examples. I've got two more to do, and you can sign out whenever you want. I don't think there's anything particularly different except for the last one. You should stick here for the last one because there's something unusual on the last one. Let's take a look at two more examples. So if I have this differential equation, the corresponding characteristic equation has constant terms, so I can use my my m squared minus 2m plus 1 method to solve, which that's going to factor into m minus 1 times m minus 1, right? So I have an m equals 1 repeated, which means yc is going to be a constant e to the 1x plus a constant times x e to the 1x, right? And so my particular, or my yp solution, will be replace those constants with functions, and then x e to the x here. And then we'll go solving those things. So we know u1 prime has to equal the Wronskian, which is e to the x e to the x, and then the derivative here is e to the x. Let me do the derivative of this on the side. So what's the derivative of x e to the x? It's going to be first times derivative of the second plus second times derivative of the first. So this is going to be x e to the x plus e to the x. Okay. And then the same determinant up here, except with the first one replaced with the right-hand side here. So I've got 0 and then e to the x over 1 plus x squared. And then this is still the original x e to the x and x e to the x plus e to the x. Okay. All right, so on the bottom, the Wronskian is this times this. So if I take this times this, that's an x times an e to the x times an e to the x, which is an e to the x plus x, which is 2x. Plus I have this times this, which is e to the 2x, minus this times this, which is an x e to the 2x. So it looks like these cancel, and I'm left with just e to the 2x on the bottom. Okay, on the top, I've got 0 minus this, which is going to be an x e to the x over, or e to the 2x, because there's an e to the x times e to the x over 1 plus x squared. So that means we've got negative x e to the 2x over 1 plus x squared. So if you factor an e to the 2x out on the top and bottom here, what you're left with here is negative x over 1 plus x squared, and on the bottom you're left with 1. So this ends up being negative x over 1 plus x squared. Okay. All right. And now let's find u2 prime. u2 prime is the same Wronskian, so it's going to end up with e to the 2x on the bottom. But here we would have the original Wronskian here, and we would replace this column now with 0 and e to the x over 1 plus x squared. So on the top here, we're going to get this times this, which is e to the 2x over 1 plus x squared minus 0. So when you factor and cancel these out, you're going to end up with 1 over 1 plus x squared this time. Okay. So now we have to take the derivatives or antiderivatives of those. So u1 is going to be the antiderivative of, let's see, it's negative x over 1 plus x squared dx. Let's do a u substitution with the entire denominator as u, 1 plus x squared. That would mean du is 2x dx, and therefore x dx is equal to 1/2 du, right? So if I take this x dx and replace it, this is the same as the antiderivative of negative. I'll bring it outside. And this is just going to be 1 over u. And then this is 1/2 du. So I'll put the 1/2 out here, du. So we end up with 1/2 natural log of the absolute value of u, but u is 1 plus x squared. Okay, so we were able to do that with a u sub. And then for this one, u2, it's going to be the antiderivative of 1 over 1 plus x squared. U sub isn't going to work there, but if you look this up in an integral table, it turns out that that's the inverse tangent of x. So you are allowed to use an integral table here. All right, and that means that my yp is going to be u1, which is 1/2 natural log of 1 plus x squared, and then times e to the x. And then I'm going to plus u2, which is the inverse tangent of x, times x e to the x, which makes the entire solution the constant e to the x plus the constant x e to the x plus this. X e to the x. All right, so there's the final solution there. Crazy, right? These can be, I mean, this method really works most times, but it can get to be really hairy depending on how complicated the right-hand side is, because depending on how complicated this term is, this can be really hard, produce integrals that are very hard to do. And the last one we're going to do is one where we can't actually solve the integral, so we'll show you a method to handle that. Let's say we had this, we have characteristic equation here, m squared minus 1 equals 0. So m squared equals 1, so m is plus or minus 1, plus 1 minus 1. So my yc is going to be a constant times e to the x plus a constant times e to the negative x. Okay. which means my postulated solution here will be a function times e to the x plus a function times e to the negative x. All right, so u1 prime would be, the Wronskian is e to the x and e to the negative x, so it's e to the x for the derivative and negative e to the negative x. On the top we have this doesn't change, but this gets replaced with 0 and 1 over x. So we've got negative e to the x plus negative x is 0, so that's going to be just 1, minus e to the 0. So this is going to be -1, so it's -2 on the bottom. And this will be 0 minus e to the negative x divided by x. So this is negative e to the negative x over x. So I could write this as positive 1/2, and it's a 1 over x, and it's an e to the negative x. Okay, u2 prime is going to be the same denominator, but it's going to have e to the x here, and this column replaced with the 0 and the right-hand side function. So on the top, we're going to get e to the x over x minus 0. So this one ends up being negative 1/2, 1 over x e to the positive x. Same thing here, except with a positive x. Okay, so when we get ready to do the integral here, like we do u1, is the integral, so we have 1/2 integral of 1x e to the negative x. There's no method that we can use, like by parts substitution, anything that will work, and it's not a form that's in the integral table. So the way we finish this off is we use the fundamental theorem of calculus. Let me go off on the side here and say, we know with the fundamental theorem of calculus that we can say g of x is an integral from some starting value to x of f, where we have a different parameter of integration, as long as this is the antiderivative of this function, right? All right, so we can kind of express that way. And so what we're going to do is we're just going to take this and we're going to say this is equal to 1/2. And we're going to say this is just some starting value 2x, where this is the integral 1 over t e to the negative t dt. Okay, and we'll just leave it in that form, meaning that if somebody wanted to, they could use that form to use some kind of a numerical solution with a computer to find that, because it's ultimately the area under this curve from some starting value to an end. Okay, and then similarly, we would just say u2 is negative 1/2 and the integral from some starting x to x of 1 over t positive e to the positive t dt. So that means our yp is all of that times, well, I'm just going to write out the final answer because there's a lot of writing here. So the final solution here is we have our C solution for the homogeneous equation, but then we're just going to take this times e to the x. So I'm just going to express that as plus 1/2 e to the x, and then an integral from some zero from x0 to x of 1 over t e to the negative t dt. And then we've got our u2, so that's going to be minus 1/2, and then e to the negative x, and then this integral x0 to x 1 over t e to the positive t dt. So you can express a solution this way, but only if you're unable to evaluate the integral with a table or with by parts or with u substitution. All right, so that should be it for section 4.6.